Hello everyone, welcome to our differential equation class. In this video we are going to talk about forced oscillations without friction. By that we mean that we have a system that is a mass spring system. So we have a spring and then we have a mast attached to the spring. So this has a mass m, this is a spring with spring constant k, and to that system we are going to act with an external force. So we are going to put here an external force of the form f of t, and we are going to study what happens when this external force f of t is an oscillatory force. It has a frequency that we are going to call frequency omega. This is going to be called the driven frequency of the force. And when we have a mass spring alone without any force, this system here has its own frequency that has a natural frequency, let's call omega 0. And what we want to do is we want to study what happens with the spring when we attach this external force with frequency omega. The whole system is called undamped forced oscillations. These are forced oscillations because we have an external force on the system, undamped because we don't have any friction, so the system oscillates without damping. And we are going to study two main cases here. One case is when the driven frequency is somehow similar to the natural frequency of the system, and then in that case the phenomenon of beats appears. We are going to describe what that is, and then we are going to study the case when the driven frequency is exactly equal the natural frequency of the system, and in that case we have what is called resonance. So to understand beats and resonance in a system like this is the plan for the video today. Okay, let's introduce our system with undamped forced oscillations. As we mentioned before, the system is going to consist of a spring with spring constant k. We are going to keep k arbitrary, and that spring has attached an object of mass m. We also keep m arbitrary, and in general there is a friction between the object and the floor, and the friction coefficient, let's call it d. D is always bigger or equal 0. In real life is always bigger than 0, but sometimes it's small, so it's important to understand the case d equals 0, and that case d equals 0, no friction, is the case we are going to focus later in this video. But for now, when we introduce the system, we keep the friction coefficient non-negative. This is the mass spring system, and to that system we are going to act with the force f of t, which is going to be an external force to the system, to the spring. And we are going to have a few assumptions on that on the system. First of all, before introducing the assumptions, what is the equation that describes the system? Well, this system is described by Newton's equation. So Newton's equation is an equation that relates the acceleration of the object with mass m with the forces. There is a force of the spring, and there is the external force, and there is the friction force. If we put all together, in a previous video we have seen that we can write Newton's equations in this way. In the previous video we studied the case when the external force is 0, and that was the equation of motion for the spring. The mass times the acceleration plus the friction force here, the damping coefficient times the velocity, plus the spring force, which is the spring constant times the displacement, all that add up to 0 in the case that we don't have external forces. And now, because we have an external force, all those terms add up to the external force. This is the equation that describes the system, and now, yes, now is when we can go to the assumptions in order to study a particular case of this system. And the first assumption is what we said before. We are going to study oscillations. The force is going to be an oscillatory force. So oscillatory external force, which means this force is of the form some constant, some amplitude, times a cosine of omega t. This omega is an important parameter. This is the frequency of the force. So that is, it has a name. It's called the driven frequency here. The driving frequency, and we're going to see that the system behaves in many different ways according to whether this what are the values of this driving frequency. The other assumption is what we mentioned before, no friction. So that means this equals 0. So that means that term is not in the equation. So and then we are going to look for solution of that system with particular initial conditions. And since we are interested in the effects of the force, we don't want to add new behaviors because of the initial conditions. So we are going to consider a system that initially is at the equilibrium position and at rest. So everything that happens to the system has to do then with the external force, and this is what we want to study in this video. So with all that, we can write down what is the problem we want to solve, at least the first version of the problem. And the problem we want to solve is find the solution. We know that there is a unique solution. Find the solution to the following initial value problem, which is the differential equation above. Now we introduce already the assumption that we don't have friction because that term is not there anymore, and we already introduced the fact that this force is going to be an oscillatory force. Is right there, and then we want to study the effects of that force. So no initial condition, initial position 0, and no initial velocity 0, and we are going to keep the constants mass, spring constant, driving frequency, and amplitude of the force amplitude. We are going to keep them arbitrary. So positive numbers, but arbitrary numbers. So that's the problem. So the big challenge for us is to try to solve this system when we have these arbitrary constants. We need to consider these letters here as fixed numbers, that it can be any number, but it's a fixed number. So when you solve this system, think, for example, that you have a 2 here, you have a 3, you have a 4, and you have a 5. So you could solve this system with these numbers, or you can solve this system with, for example, 3 here, a 2 here, a 1 here, and a 7. So instead of giving a particular set of numbers, we just keep them arbitrary, but they are constants. So one more time, this is just a number that happens to be called m, but it's a number. This is a number that happens to be called k, f0, and omega. These are just numbers. So when you see that, it's nothing more than constants here. So it gets sometimes one needs sometimes to get used to that, but they are just constants. And before we start, because we have all these constants here, and we can actually simplify the constants a little bit and introduce more meaningful constants. Before we start, we rearrange the constant in the equation. And how we are going to rearrange the constants? We are going to divide the whole equation by the mass of the particle, of the object. So the mass is going to enter here, there, and there. So what we are going to do is we are going to rewrite the equation as y double prime plus, and then we have here k over m y, and this is going to be equal f0 over m cosine of omega t. The omega doesn't change. And here let's put the line over there. So that is going to be our system. So now this number, actually this one here, is going to be important. And actually this is a positive number because k is positive, m is positive. So we are going to write it as in the square of something. And what we are going to do is we are going to write it as k over m is going to be omega square, omega 0 square. So we define, so we introduce the number omega 0 as the square root of this number here, which is well defined because that number is positive. That number is called the natural frequency of the system. So why is the natural frequency? We are going to see that in a minute. But essentially, when you have zero force, when this amplitude is 0, this is the solution of this equation is going to be an oscillatory solution, sines and cosines, and they're going to be sine and cosine of a frequency times t. Well, the frequency is going to be omega 0. So that's why this number is important. And we introduce another constant, which is the amplitude divided by the mass, which we call it that was the amplitude capital F. Well, this is going to be small f, lowercase. So with that, we can rewrite a little bit the equation in a little bit nicer way. But before that, one remark. Why we call this equation, so now we are going to do it in writing, why this is the natural frequency of the system? Well, because in the case of no external forces, this f is 0, so we have this equation, and if you solve this equation, we already know how to do it. You just put exponentials in here, exponentials rt, that is going to give you a characteristic polynomial r squared plus omega 0 squared equals 0, and that means that r plus minus is going to be pure imaginary plus minus omega 0, that's why we put the square, omega 0 I, and that means that the fundamental solutions are real valued, are sine and cosine functions. So that calculation gives us that the general solution of the homogeneous equation is a combination of cosine and sine of omega 0 t. So the system oscillates, these are oscillations, with the frequency omega 0, and omega 0 is what we introduce here. So that's why this is called, omega 0 is called the natural frequency of the system. It's the frequency that the system is going to oscillate when it's left alone. So when the system is left alone, oscillates with frequency omega 0. So let's rewrite now our problem one more time with the new notation. Our problem looks like this. Solve this equation. Now we are all the parameters on the equation reduced to the natural frequency, and here we have the amplitude of the forced oscillations and the frequency of the oscillation. This is recalled the driving frequency, this is the natural frequency, and we want to study the effect of the force, so 0 initial conditions. And now we have two parameters in the equation, in our problem, the natural frequency and the driving frequency. So it turns out that the solution of this problem depends a lot on what values for the driving frequency we choose. And there are two main cases. The first case is when the driving frequency here is different from the natural frequency. So let's put it in words. Driving frequency is different from the natural frequency. In that case, well, there are two main situations. One when they are very different, and the other is when they are really close. When the driving frequency is close to the natural frequency, and in that case we are going to have a phenomenon that we are going to call beats. which we are going to describe later on. And that happens when the driving frequency is close to the natural frequency, but different. Close but different. And then the other case, well, you know, the other case is when the driving frequency is actually exactly equal the natural frequency. This is what we have here. And in that case, we are going to have a different phenomenon that is called resonance, which we are really interested to understand. Okay, so this is the summary of what we are going to do in this video. Okay, let's start with the first case above. We have our differential equation, we have our source, and we are going to consider the case omega, driving frequency, different from the natural frequency omega 0. So let's try to sketch the solution. So we are not going to do all the calculations. We are going to leave some calculation for the viewer, but what do we need to do to solve this problem? Well, one thing we need to do is first solve the homogeneous equation, isn't it? We need to solve the homogeneous equation. And what is that? Well, it's the equation we mentioned before. We need to find a function yh, solution of the second derivative plus the natural frequency square yh equals 0. And how do we do that? If you recall, what we need to do is we propose solutions of the form exponential rt that give us the characteristic polynomial r squared plus omega 0 squared equals 0. From here we get that r plus minus is going to be plus minus the natural frequency times I, and that implies that the exponentials, if we use the Euler formula for pure imaginary exponentials, is going to be, the solution is going to be linear combinations of cosine of the natural frequency times t plus sines, so another combination of sines of the natural frequency times t. Whatever the natural frequency is, we know what it is. The natural frequency, of course, is the square root of whatever the spring constant is divided by the mass of the object. Whatever this number is, determine the natural frequency, and that is what goes in there. So once we found that, the second step here is to solve that problem, is to find a particular solution. Find yp of t is a particular solution, of the non-homogeneous equation and the non-homogeneous equation is, let's write it as L of yp equal the force, which in this external force, which is F0 cosine driving frequency times t, and we are using the notation, the usual notation, where all this left hand side is what we call L of y. So well, so L of y has the natural frequency inside. Alright, so we, given the right hand side, we guess what is a particular solution. We guess y particular of t, and here is an interesting thing. So we are going to guess k1 cosine of omega t. And we are going to find k1. k1 is the undetermined coefficient in our guess. We are going to put this function in here, and the equation is going to determine what is the constant k1. And notice that this is a good guess in the following sense. Good guess up here. Guess, because what happens when we put that function into the operator, the differential operator? Well, we are going to have a second derivative of the cosine, which is going to be k1, and then negative, and then omega one time, the second derivative another time, so omega square cosine of omega t, and then we have the term plus omega natural frequency square, and then the function, which is k1 cosine of omega t. Notice that this in this calculation we can pull common factor the k1, we can pull common factor cosine of omega t, and then we have everything multiplied by minus the driving frequency square plus the natural frequency square. And this is different from 0 because this factor here is different from 0 because we are assuming that the driving frequency is different from the natural frequency. Because of that, this is different from 0, and therefore this function is not solution of the homogeneous equation. So it's a good guess. Now you may notice that our guess did not include a constant k2 sine of omega t. Why? When last class we said that we should always put both. Whenever you have a source that is cosine or you have a source that is sine, we said for a general differential operator you have to guess both. Sine, a combination of sine and cosine with the same frequency. And now we are not guessing the sine term. So why is that? That is explained in the following remark. If you have a differential operator on the left hand side that is of this form with second derivatives, first derivatives, and the original function, and then you have a source like that on the right hand side, then yes, then we must guess both terms. Both terms, yes, cosine and sine. But when we have d equals 0, when this term is not there, this is what we say here, when d is equal 0, so the differential operator is like the one we are working with in this calculation, then you don't need the sine term. Only the cosine is enough to find a good particular solution. And the reason is, when you have the first derivative, what it does, it mixes both sine and cosines. If your guess is cosine only, and you have this first derivative, then you're gonna, that first derivative is gonna, when you put it here, is gonna create a sine. And that means that if you guess only cosine, here you're gonna get a cosine, the source is gonna be a cosine, and then you're gonna create a sine that is, you cannot equal to anything, that is the only sine term. So what happens is, when this term is here, this cosine is not enough, it's not a good guess. You need both terms with a sine. So when this term is here, you need to guess both. When this term is not there, then you need to guess whatever is in what you have on the source. In this case, we have a cosine, so the cosine is a good guess. So we have a cosine here, so a cosine is a good guess because our operator, our differential operator, doesn't have the first derivative. So that's why. Alright, so now that we understand that, the calculation is going to be simpler than usual because our guess is simpler. So this is our guess, is a good guess, and because of that is the perfect guess. So now you put that into the differential operator, and like we did here, and now you find the constant k1. And what you're gonna see is that the result, this calculation, we leave it as an exercise, and the result is the constant k1. Let's put k1 here to be consistent. The constant k1 is going to be given by the amplitude of the force and the difference of the squares between the natural frequency and the driving frequency. So this is a constant. Recall that it looks complicated, it looks like a function, but actually, recall, we are fixing numbers. This could be a number 7, this could be a 2 square, and this here could be a 3 square. So this could be, for example, 7 over 4 minus 9. So this could be a 7/5 negative. So it looks complicated, it looks like a function, but these are just names for constants, so the whole thing is a number, it's just a constant. Okay, so this is the solution. So now we have the particular solution here. We have the general solution of the homogeneous equation there. So notice that in the homogeneous equation we have the natural frequency, and in the particular solution we have the driving frequency, and then here appears both in the amplitude. So now that, we have the general solution for the whole equation, which is going to be, well, the solution of the homogeneous equation, C1 cosine of omega 0 t plus C2 sine omega 0 t plus that function, which, recall, this is a number divided by another number. This is the number multiplied by the cosine of the driving frequency times t. So this is the general solution to our problem. And now we need to impose the initial conditions. Recall that our problem has initial conditions, which is both function and derivative at the time t equals 0 are 0. Okay, exercise, impose the initial conditions. The initial conditions are going to fix these constants, C1 and C2. And for those initial conditions, what is going to happen is that C2 is going to be 0. The term is not going to be here. And that is going to be equal minus this number here. That is what is going to happen. And if we put all that together, you need to prove in the next exercise that the initial conditions imply that this is the solution of the initial value problem when we have a driving force with the driving frequency omega, and our system has a natural frequency omega 0, and then it's going to be the solution of that initial value problem is the difference between these two oscillatory solutions with amplitudes, one with amplitude given by that number, the other with amplitude given by the negative of that number. So exercise is not difficult, prove that. Notice that the solution that we just found is not defined when omega is, so the driving frequency is equal to the natural frequency, because in this case, obviously what we get is, well, the denominator is 0, but also here the numerator is 0. So we get that our solution is not defined at all, is something of the form 0 over 0. So this solution is not defined when the driving frequency equals the natural frequency. But it is defined for any other driving frequency, and what we are going to do now is we are going to study what happens when the driving frequency is very close to the natural frequency. What happens when the driving frequency is close to the natural frequency? Well, we get the phenomenon of bits. So what do we mean by close first? well, this is a good definition as any of close. The solution, the function in equation 2, recall the equation 2 is our solution here. You see we have a difference of two cosines with different frequencies. And now suppose these two frequencies are very close to each other. How close? Well, they have to be as close as the close within a 1% of so the difference between the values divided by one of them, for example the natural frequency, should be in absolute value that difference smaller or the order of 0.01. So 1% distance between the two frequencies. When that happens, we see a very strange behavior in the solution. When the driving frequency omega is close in this sense to the natural frequency, then the solution which is the difference of the two cosine, and notice that we are dividing by that, so that factor becomes very close to 0, which means this is really large because the 0 is in the denominator, but we also have that is close to 0 also. The combination of all that produces a solution that looks like this. So this is the solution we are making the graph of, and the solution has oscillations, and there is also a modulation in the amplitude that creates this behavior. So this is a graph constructed with particular values. The important values here is I fixed the natural frequency to be 5 and the driving frequency to be close to 5 within a few percent. So here I need to change the name. This omega here is what I call here nu. So in this program, now pretty soon we are going to go to that program and we are going to see how this picture is constructed. But this is how the solution behaves, and this strange shape, this modulation in the amplitude, is what we call bits, and we are going to understand why it's called that way. So let's put that in writing. This modulation is amplitude, and this happens when omega is close to omega 0. So now we are going to go to the program where we did this picture, and we are going to go a little bit more in more detail why this happens. If you have access to our D2L class, you can go here and go to interactive graph. I think you go there, and after you go there and the page loads, there are a few interactive graphs here using GeoGebra program, and then some using Math Studio program. Well, this is the one you need, and you need to click here in bits and resonance. I already did. It takes a while to load, so it's loaded here. So you are going to recognize the solution we are working with. It's right here, and if you click in the Math Studio link right there, you're gonna be, this is the program I use to compute the graph that is down here, and so we don't see anything. So okay, so the first thing we need to do is, this is the non-resonant solution, so we turn it on. You see it's purple here. We need to put some amplitude, so we have this is f0, and nu here I'm gonna change it sometime with omega. This is the driving frequency, so we need to increase the driving frequency. This program assumes that, let's read over here, that omega is 5. You see this omega? This omega actually is omega 0 in our convention. This is the natural frequency, is 5. So you see the driving frequency is far away from 5. There is no patterns here that we can discern, and when we start closing to 4.5, that picture emerges. This is the picture we mentioned in the notes. That is bits. So the idea is now why this this function, this graph shows up. And recall that what we are doing is, let's go back here. What we are doing is we are graphing this function, which is a difference of two cosines with that same amplitude. So what we are going to do now is we are going to plot each of these terms. So the solution of the homogeneous equation is the one with the natural frequency. Is going to be plotted in green with the negative sign that appears here. And then we are going to plot in red the other term, the first term. So if we do that in our little picture, so this is the particular, let's plot the solution of the homogeneous equation with the natural frequency. There it is. It's kind of hard to see, so what we are going to do is we are going to kill the resonance solution, the sum. It's a cosine with a frequency 5. That's all it is, and some amplitude. The other solution, the particular solution, has a very similar frequency, not exactly 5. It has 4.568, but same amplitude. So here it is. So for example, here you see that both solutions coincide. But then because the solution in red has a slightly different frequency from the other solution, it starts to get out of phase. And at some point here, you see it's completely out of phase. And then the same thing happens and become on phase again, and out of phase, and phase again, and so on. Because we are adding these two solutions, recall the solution in green, the graph in green here already has the negative sign in it. So we are adding these two solutions. What is happening is here the two solutions add up, and here the two solutions, they subtract, and you get 0. And this is what we see in the solution here. You see when both green and red solutions have the same values, you have a large value for the sum. When they have opposite values, well, we get 0. And that happens with forever. So we have this pattern of great amplitudes going to 0, great amplitudes going to 0. And this is always happens when you add two frequencies with the same amplitude, and one frequency is slightly different from the other. The closer we get, the bigger is the addition, and then they are going to go to 0. So now we can take out the other two solutions, each term, and we get only the bits. So at the beginning it's kind of nonsense, the frequencies are too far apart, but when the frequencies start to get closer, you get this modulation in the amplitude of the high frequency solution. So that is what is called bits. Now we are back to our notes, and what we just saw in the interactive graph. Here I have some static pictures. Here is what we saw in the interactive graph. We are plotting one term of the solution in red, is this function here. The other term with a negative sign is in green, is in here. We are plotting, recall this nu here. This nu is this is gonna go away. Yes, I knew it. This nu is actually the driving frequency, and the picture here is for omega 0 equal 5. So when the frequencies are very close to each other, so at some points they are the maximums are the same, but a little bit later the maximum have opposite values. So here the addition is 0. Here they add up to a large value. Here they add up to 0. And if you see that together with the addition, that is the reason that here we have the big values of the sum, and here 0 values. And that happens when the two frequencies are very close. When the frequencies are far apart, then you just get something without any pattern. So now we can even listen to the bits, because if this behavior happens with two frequencies for sound waves, we can actually hear this behavior, and the reason why it sounds that way is why it's called bits. So now what we're going to do is we're going to go to a wave generator, a sound generator, and we're going to put two frequencies which are going to be identical. Then we don't have bits. Then we are going to have different frequencies but very close, and we are going to hear this behavior. So here we are with our frequency generator. So here we have we are going to generate a sine wave. So sound at 3 Hertz is going to be that kind of loud, but let's put it like this. Okay, something like that. And of course here we are going to have exactly the same sound. So, and what happens if we put this is there, and what happens if we put them together? Well, we are going to add this same. There. Now they are adding. Okay, and now what happens if we move the frequency of one of these sounds a little bit off? For example, 2 Hertz. 1% should be 3 Hertz. Okay, 1% away. So the sound is going to be pretty similar. We're not going to notice a difference. It's very similar to that. But now when we put them together, that's the beats. So we can move the difference between the two sounds, the frequency. No beats. Very long beat. We just don't hear when the other frequency is too far away from the original frequencies. Let's suppose this is the natural frequency. When the driving frequency is too far away, well, then there's nothing we can do. So there was here. Okay, let's see. There it is. This is the way to put back 300. Or 303 there. So this is our beats. Well, and that is beats. We have here this where is it? This oscillation. So the background sound is given by this frequency. These are the 300 Hertz, and here this is the beats with a very much larger frequency that we were hearing. So now let's move on to the last case, and the last case is when we have the driving frequency exactly equal the natural frequency of the system. So what is going to happen in that case? Well, recall our solution. The solution that produced the beats when the driving frequency is close to the natural frequency producing the beats is not going to be defined here anymore, because we are going to have 0 over 0. But what happens when we get closer with that driving frequency to the natural frequency? Suppose we, instead of 4.55, we are a little bit closer, 4.7 for example. then we are gonna get something like that. So what is happening is and we heard that when we were listening to the sounds, the beats, the frequency of the beats gets larger, so the frequency gets smaller of the beats, so the wavelength is larger. Recall when there was only 1 hertz of difference, we hear a beep, 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 but when they were 3, we heard beep, 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 beep. So that means this when the difference is larger between these two frequencies, that wavelength is smaller, and then that wavelength gets larger when we are closer to the natural frequency, and it's gonna get larger and larger the closer and closer we get. So this is gonna go something like this for closer. So it's gonna be something like this, or even closer, it's gonna be something like that. But notice that the amplitude start to diverge here. So can we see that analytically? Sure, we can, but what we need to do is we need to solve the problem for driving frequency omega exactly equal the natural frequency. And recall the solution that we already had is not defined. So we need to solve the problem again, but now this time with there. But now this time with natural frequency inside the driving frequency. Before here we had omega. Now we have omega 0, which is the same omega 0 we have there. Okay, how do we solve this problem? In the same way we solved the other problem, but we need to be a little bit more careful. Solution. What do we do here? Well, we need to solve the homogeneous problem again. Recall that was the first step. So the first step, solve. That's an ugly E. Solve, and an ugly V. Solve the homogeneous equation first. We did it already. Well, the homogeneous equation is L of YH equals 0, and of course, as always, this is L. So, and we got that solution, so we are gonna write it down again here. It's a linear combination of cosines of the natural frequency of the system times t plus some other constant sines of the natural frequency times t. Okay, we got that. So now we need to solve the non-homogeneous equation. So the non-homogeneous equation, and this is the equation L of, and we need to look for a particular solution, but the equation is L of y equal that source, and now the source unfortunately has the natural frequency in it. There. So what is the solution of that? Well, we are going to guess a particular solution. We guess, and our guess is, if we have something like that, and recall we don't have the term with the first derivative, so what we did before is, we guessed a particular solution here, a particular solution y of t equal some constant cosine of whatever our source is. In this case is omega 0 t. So if we guess that, well, that is going to be the wrong guess now. And why is that? Because this function here is solution of the homogeneous equation, because we are using the natural frequency. And even if we put the other term that we shouldn't need to put it, but if we put the other term here, sine, is not going to fix the problem, because the other term is also, is also solution of the homogeneous equation. So this is the ground guess. So this one here is ground guess, and we are going to call it first guess because we're going to need to do a second guess. This is ground. Is the ground guess, that is an ugly E, because as we mentioned, L acting on this function is actually 0, is solution of the homogeneous equation. So what do we need to do? We need to multiply by t our first guess. So what we need to do is a second guess. Okay, what is going to be the second guess? The second guess, P2 of t, is going to be t times the first guess. So recall that we put only the cosine. Okay, k1 t cosine of omega t. But this is going to be the ground guess for a different reason now. This function t is going to actually is going to mix sines and cosines. It's going to create some non-trivial terms. So actually this is going to be the ground guess, and what we are going to need to do is actually multiply by t this guess, the guess that contains k1, oh sorry, and k2. This should be different constants, k2. In general they are different constants. So actually the correct guess now, by trial and error, you can see that it's going to be k2 t sine of natural frequency times t. So now this is going to be a good guess. How you know it? In advance you don't. You need to put it into the equation. If you put into the equation only that, it's not going to work. You're going to need to put both. So do the calculation, is left as an exercise, and you're going to end up that this is a good particular solution. And not only is a good particular solution, this is the particular solution too. This is actually the solution of the initial value problem, because this particular solution happens to satisfy the initial conditions. Look, at the t equals 0, both sine and t vanish, and the derivative, well, the derivative contains sine, that is going to be 0, and then contain a term that is going to have a cosine, but with a t. The derivative, this t vanishes, so check that this function also satisfies the initial condition, so is the solution of the whole problem in equation 4. Equation 4 is not only solution of particular solution of that, is the whole solution of the problem. It satisfies the initial condition. We got it for free. The particular solution we were looking for has k1 equals 0, k2 equal f0 over 2 omega 0. Again, this is an exercise. And because of that form, t sine, it satisfies the initial conditions. So how does it look like, this solution? Well, here it is. It's a solution that has an amplitude that increases in time with the factor t. So here it is. This is the factor t with this slope. And it's a sine function because it starts at 0 and then oscillates with the natural frequency, which is 5 in this picture. But the amplitude diverges in time. And if you recall the bits solution when we were approaching the driving frequency to the natural frequency, and we overlap, this is what is happening. What is happening is that the bit solution start to get closer and closer to this solution here. And we can see that behavior in our interactive graph. We are back to our interactive graph, and now we need to go to the bottom where we can press, where is it? Is down here, and this is the resonance solution in blue. And there it is. This is the resonance solution for the parameters in our system. Is overlapped with the bit solution, and now if we grab the driving frequency and we start getting closer and closer to the natural frequency, we see how the one solution start matching the other. So this is how we get, and now we can zoom. Oops, can I zoom? Okay, what did I do? And now we need to put everything. Oh, let's put the resonance solution. I shouldn't have touched that too much. Let's put some frequency there and some amplitude. And now we get closer and closer, and look what is happening. We have the bits solution is developing the bits, and then the bits start approximating the resonance solutions. And now this is what I wanted to do. You can zoom all the way you want, but the oops, it's kind of closer you get, and there you are gonna get the approximation at some point. And this is how the bit solutions approximate the resonant solutions. Now let's go like that. So, in summary, we see that in the graph above, let's put it in writing, the bit solutions approximates the resonance solution when the driving frequency approaches the natural frequency from these two pictures. And we also see that the resonance solution diverges as function of time. As function of time, that means now if we look only at the resonance solution, the oscillation starts small and then start increasing, and they diverge in time because the solution has this factor t here. That is saying that the solution is gonna diverge in time. So what is the meaning of that divergence in time of the amplitude of the solution? Well, resonance is gonna break whatever system is you are describing. So when the driving frequency is exactly the same as the natural frequency of the system starts oscillating until it breaks. So, however, in real life, we don't see that every system get destroyed when we apply a force with the same frequency as the natural frequency of the system. What happens in real life that is not described here? Well, the problem is that our description has no friction at all. Recall, this was our first assumption. It turns out that in real life, all systems actually have friction, and friction actually tames the effects of resonance. So you're still gonna see at the resonant frequency, when the force has the frequency of the natural system, you're gonna see increase in amplitude, but because of friction, it's gonna be finite, and most systems are not gonna break. Some systems will do when the friction is small enough that the system breaks before achieving an equilibrium. So that's why not every system breaks in nature when the external force oscillates at the natural frequency of the system. So in the textbook, we are going to have a part of the section dedicated to computing the formulas in the case that we have the system we described plus friction. And we are going to see this taming, this non-breaking of the system when we have a force with the frequency equal the natural frequency of the system. We are going to see that in this case, when we have friction, the system doesn't break. And if you are interested, you can look at the textbook. We are not going to cover that this particular case in our class because the calculations are kind of fairly complicated for one lecture, but it's going to be in the textbook. So this is what we wanted to mention about solutions with the system of a mass spring system with an oscillatory force that has a frequency, driving frequency, that is different from the natural frequency or equal to the natural frequency, where we have beats, or when both frequencies are close but different, but close. And when both frequencies are identical, then we have the resonant solution. So that's it for today. See you guys in the next video.